day. Today we're going to discuss the evaluating determinants by row reduction. So in this discussion, we will show how to evaluate a determinant by reducing the associated matrix to row echelon form. So in general, this method requires less computation than cofactor expansion and hence is the method of choice for large matrices. Okay, so let's have the basic theorem. We begin with the fundamental theorem that will lead us to an efficient procedure for evaluating the determinant of a square matrix in any size. So theorem 2.1.1, let A square matrix. If A has a row zeros or a column of zeros, then the determinant of A is equal to 0. Okay. Then we also have the theorem 2.2.2. So let A be a square matrix, then determinant of A is equal to the determinant of the transpose of A. So because transposing a matrix changes its columns to row and its rows to column, almost every theorem about the rows of the determinant has a companion version about columns and vice versa. Okay, so let's have the elementary row operation. So the next theorem, which is this one, um, shows how an elementary row operation on a square matrix affects the value of its determinant. So you have here, let A be a n by n matrix. So if B is a matrix that results when the single row or single column of the A is multiplied by the scalar k, then the determinant of B is equal to k times the determinant of A. If B is a matrix that results when the two rows or two columns of A is or are interchanged, then the determinant of B is equal to the negative determinant of A. And if B is the matrix that results when the multiple of one column of A is added to the another column or when multiple of one column is added to another column, then the determinant of A is equal to the determinant of B. The have let's have this one. Okay, so in this table, okay, the first panel shows that we can bring a common factor from any row or column of the determinants, although the determinant sign, not although, through the determinant sign. This is a slightly different way of thinking about the first theorem that is on the previous slide. Okay, now you have here the operation. Okay, so this is actually the table where the illustration of the theorem 2.2.3 is presented. Okay, so of course you have the first row of A is multiplied by scalar k, and then the first and second rows of A is interchanged, and then a multiple of the second row of A is added to the first row. So actually, this is the illustration of the theorem presented on the previous slide. Okay, so let's have the theorem 2.2.4. Okay, in elementary matrices, it will be useful to consider the special case of the theorem 2.2.3, in which the A, the matrix A, is equal to its identity n. Okay, in uh, n by n identity matrix, and E rather than B denotes the elementary matrix that results when the row operation is performed on that identity matrix. In this special case, the uh, the theorem 2.2 uh, 2.2.3 implies this theorem 2.2.4. So you have here, let A be an n by n matrix if the elementary matrix E results from the multiplying a row in identity matrix N of by a non-zero number K, then the K, uh, not the K, then the determinant of E is equal to K. Okay. And then if E results from the interchanging two rows of the identity matrix N, then the determinant of E is equal to negative 1. And if the E results from adding a multiple of one rows of the identity matrix N to another, then the determinant of E is equal to 1. Okay, so let's have this one. Now, the following determinants of the elementary matrices, which are evaluated by inspection. Okay, which illustrates the theorem 2.2.4. So observe that the determinant of an elementary matrix cannot be zero. So you have here on the leftmost of the illustration, the second row of the I sub 4 was multiplied by 3, so which is equal to 3. Okay. And then the first and the last rows of the I sub 4 were interchanged, which if you are going to get the determinant, then that would be negative 1. And then 7 times the last row of the I sub 4 was added to the first row. Well, if you are going to get the determinant, then that's equal to 1. Okay. So matrices with proportional rows or column. So if a square matrix A has a proportional rows, then the row of zeros can be introduced by adding a suitable multiple of one of the rows to the other. Similarly, the columns, uh, this is also applied for columns rather, but adding a multiple of one row or column to another does not change the determinant. So from the theorem 2.2.1, we must have the determinant A equals 0. So you have the theorem 2.2.5. If A is a square matrix with two proportional rows or two proportional columns, then the determinant of A is equal to 0. Okay. So let's have an example. So you have that one. As you can see on this example, okay, you have a proportional row. So the first row and the second row are proportional with each other. So in this case, the um, the second row is two times the first row, as you can see. So we added negative 2 times the first row to the second to introduce a row of zeros. So in this case, you could have um, you could have 1, 3, negative 2, 4, and then um, if you have uh, negative 2 times the first row, then add it to the second, then you have, of course, 0, 0, 0, 0. Then you have 3, 9, 1, 5, and then 1, 1, 4. Then that would be equal to 0. Okay. So each of the following matrices has two proportional rows or columns. Thus, each has the determinant of 0. Okay. So let's have evaluating determinants by row reduction. We will now give the method for evaluating determinants that involves uh, substantially less computation than cofactor expansion. The idea of the method is to reduce the given matrix to upper triangular form by elementary row operations. Then compute the determinants of the upper triangular matrix, which is an easy computation, and then relate that determinant to that of the original matrix. So here is the example that's using row reduction to evaluate a determinant. So evaluate the determinants of A, where A is equal to 0, 1, 5, 3, negative 6, 9, 2, 6, 1. So for our solution, we will reduce matrix A to row echelon form, which is uh, upper triangular. Then apply the theorem to that 2.1, that 2. So you, so you have here, okay. So here you have the determinant of A is equal to, you have 0, 1, 5, then you have 3, negative 6, 9, and you have 2, 6. Okay. So in this case, we have uh we have to, what do you call this one? As you can see, you can interchange, okay, the the what do you call this one? The first and second rows of A. So this case you have negative 3, negative 6, 9, then you have 0 and 5, then you have 2, 6, 1. Okay, so a common factor of 3 from the first row, okay, will be taken through the determinant sign. So in this case, you have negative 3, okay, then you have 1, negative 2, 3, okay, 0, 1. 5, and 2, 6, 1. Okay. And then in this case, we have negative 2 times the first row will be added to the third row. Okay. So again, negative 2 times the first row will be added to the third row. So you have negative 3. You have 1, negative 2, 3. You have um, 0, 1, 5. And then you have here 0. You have 10. And then you have negative 5. Okay. So here we have in negative 10 times the second row will be added to the third row. Okay, negative 10 times the second row will be added to the third row. So you have here, um, you have 3, then you have 1, negative 2, 3, then you have here 0, 1, 5, and then you have the 0, 0, negative 55. Okay. And then the common factor of negative 55 from the last row will be taken through the determinant sign. So determinant sign tayo. So you have here negative 3, negative 55. Okay, let's try to have this one in the other side. So here you have um, negative 3 times negative 55 times you have the 1, negative 2, 3, 0, 1, 5, and 0, 0, 1. So you have now the upper triangular, which is equal now to you have negative 3 times negative 55 times 1, which is equal to you have 165. Okay. Let's have another example using the column operation to evaluate the determinant. So you have here uh, the square matrix A. So compute the determinant of the A. So for the solution, this determinant could be computed as on the previous uh, by using elementary row operations to reduce A to row echelon form. But we can put A, okay, this matrix A in lower triangular form in step uh, um, in one step by adding negative 3 times the first column to the fourth. So you have you can obtain that you have determinant of A is equal to the determinant of you have 1, 0, 0, 0, and then you have 2, 7, 0, 0, then you have 0, 6, 3, 0, then you have the 7, 3, 1, negative 20, 6. Okay. So you have, in this case, you have 1 times 7 times 3 times negative 26, which is equal to, you have uh, 26, negative 5, 4, 6. Okay, so this example points out that it is always wise to keep an eye open for column operations that can shorten computations. Okay, so let's have this one. So two-factor expansion and row or column operations can sometimes be used in combination to provide an effective method for evaluating determinants. So let's have this one. Okay, so evaluate the determinant of the A. Okay, so for our solution, we can, uh, by adding suitable multiples of the second row to the remaining row. Okay, so we have multiple suitable multiple. So you have, in this case, so if we are going to multiply the second row by um, negative 3, then add it to the first row, then you can have, um, take note that the second row is 1, 2, negative 1, 1. So here, in the as what I mentioned a while ago, that if you multiply negative 3 to the second row, then add it to the first row, then you can have 0, negative 1, 1, 3. Now, for the third row, if we are going to multiply the second row by negative 2 and add it to the third row, okay, so you have 0, 0, 3, 3. And for the fourth row, if you multiply the second row by negative 3, then add it to the fourth row, then you have 0, 0, 1, not 7, but 1. Okay, 0, 1, 8, 0. Okay, so uh, we can use the cofactor expansion along the first column. So in this case, you have negative 1. Okay, so you have negative 1, 1, 3, 0, 3, 3, then 1, 8, 0. Okay, and then we can add the first row to the third row. Okay, so you have negative, okay, so you have negative 1, 1, 3, then you have 0, 3, 3, and you have 0, 9, 3. Okay, and then we are going to have the cofactor expansion along the first column. So you have negative times negative 1 of the 3, 3, 9, 3, which is equal to, in this case, you have negative 18. Okay, so in summary, In this video, it is discussed the effect of the elementary row operations on the value of a determinant. And then you have the you we have discussed the determinants of the three types of elementary matrices, and we have also discussed how to introduce zeros into the rows or columns of a matrix to facilitate the evaluation of its determinants. Then use row reduction to evaluate the determinants of a matrix, and then use column operations to evaluate the determinants of the matrix, and combine the use of the row reduction to cofactor expansion to evaluate the determinants of a matrix. So I hope you got those discussion. So thank you very much for